Our goal today is to review matrices and talk about their properties. Matrices. As we discussed before, when we are talking about matrices, we are basically talking about a rectangular array of numbers. A matrix is a rectangular array of numbers. So how did we define matrices? We say that, hey, when we have a matrix like A is defined by its entries, A sub I, J. We define the size of a matrix, right? For example, we have a 1 by 1 matrix. We can define simple matrices. For example, matrix A can be written with just one entry, one element. You have one row and one column. You can define more complicated matrices as well. For example, matrix B can be defined as, well, it can have elements, entries like 1, 2, 3, then 7, 8, and 9. Here we have 2 rows, and then we have 3 columns. So we say that it is 2 by 1, 2, 3 columns. 2 by 3. So this is the size of your matrix. When do we say matrices are equal to each other? Definition. Equality between matrices. So in general, when you're talking about the equality between matrices, we say that 2 matrices. One of them can be denoted by A with entries like A sub ij, and this is a matrix with entries represented as A sub ij. If it's an m by n matrix, well, remember that we could list all the entries one by one. We could write it this way: A sub 1 and 1, A sub 1 and 2, dot, 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 A sub 1 and n. Then on the second row, A sub 2 and 1, A sub 2 and 2, dot, 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 A sub 2 and n. You could continue this process and list some more entries down here. Now on the m row, A sub m and 1, A sub m and 2, dot, 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 A sub m and n. Remember that when we're talking about equality between matrices, we need to make sure they have the same size. So this is m by n matrix, and another matrix, matrix B, for example, with entries B sub ij, which is an m by n matrix again. So you could list all the entries this way: B of 1, 1, B1, 2, dot, 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 B1n. On the second row, let's just list some of these: B2, 1, B2, 2, dot, 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 B2n. And let us go to the last row: BM1, BM2, dot, 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 BMN. So we say that these two matrices are equal to each other when they have the exact same size and entries are equal to each other. And we write it this way: two matrices are equal if they have the same size. We already specified that both of them are m by n matrices. If they don't have the same size, basically there is no point setting them equal to each other. And A sub ij is equal to B sub ij when I ranges between 1 to m and j ranges between 1 to n. So the entries must be equal to each other. So A1 and 1 must be equal to B1 and 1. A1 and 2 must be equal to B1 and 2. I'm just using some random colors. A2 and 2 must be equals to B2 and 2, and so on. We can do some operations between matrices as well. We have addition, we have subtraction, we have a scalar multiplication. We also can multiply two matrices together. Just one question. Example. Are these two matrices equal? So consider these two matrices. I have matrix -1, 2, 0, 1. I'm going to add two more entries here, 0 and 0. And then another matrix is like this, -1, 2, 0, then 0, 1, and 0. I might say, okay, I'm shifting these entries a little bit here and there. For example, this is -1, then I have a -1. Then I have a 2, I have a 2. 0, 0. Then 1, okay, let me switch this one to 0, then 1, then 0. So component-wise, entry-wise, you might say, hey, I see the exact same entries. But take a look at the size. It is 2 by 3 matrix, and this is 3 by 2 matrix. So this is where we say that, hey, the same size is important. This is the case that you see two matrices like this. So again, we have some operations between matrices. Operation between matrices. What is our goal? Our goal is to create something new, right? How do we add two matrices? Let us start by a very simple operation. Matrix addition. So for matrix addition, what do you think? Do the matrices need to have the same size so you can add them together? You can type your answer in the chat for me. So do you think that having the same size is a requirement for matrix addition? It is one of the requirements. So when you're adding two matrices, they must have the exact same size. So we can formulate it this way. Let A be a matrix with entries Aij of size m by n, and then B is another matrix with entries Bij, the same size m and n. B2 matrices of the same size. What we can do? We can add these two matrices together. We can add these matrices. We denote this by A plus B. This basically generates a new m by n matrix for you, which is a new m by n matrix. So you can write it this way. If I add A and B, I'm basically adding the components of these two matrices together. Aij plus Bij. So if you break it down into smaller portion, so you can see all the details, you're basically saying that, hey, the very first entry must be added to the first entry of matrix B. This generates a new matrix for you. So here you have, let me shift this a little bit so I have enough space. My matrix on the other side needs a little bit space. Okay, here we go. A11 plus B11, A1 and 2, B1 and 2. If you add these together, you get A12 plus B1 and 2. You can continue this process. You can add more entries, dot, dot, dot. A1N, B1N, so A1N plus B1N. And then you can continue this process as I mentioned before. So this goes further down to the rest of the entries, AM1, BM1. So these two are added together and create a new entry plus BM1. And then you have, for example, AM2, BM2, AM2 plus BM2. And finally, the last one with a different color, AMN, and then BMN. So this basically gives you AMN plus BMN. So it happens that this matrix also have the exact same size as matrix A and matrix B. This is an M by N matrix. So addition of matrices is super easy. Let's go over a few examples for you. Suppose I ask you to add the following matrices. Find the sum of the following matrices. So we want to add, for example, identity matrix 1, 0, 0, 1 by 0 matrix. What is the result? So basically, you have 0 matrix. All right. When you add these two matrices together, what's your guess? What would be the final result? This is the easiest addition between matrices. If I add any matrix, like A, B, C, D, with 0 matrix, what would be the result? You can type your answers in the chat, everyone. Very good. We get this exact same matrix back. Here I have 1, 0, 0, and 1. So 0 matrix doesn't change the addition. It basically looks like a value that is neutral. It doesn't change the original matrix. So you can write it this way. Any matrix plus 0 matrix is always equal to matrix A. You can add, for example, the size to make sure we are adding matrices with the same size. So any M by N matrix plus 0 matrix of the same size result in the same matrix. You can switch the order as well. What do I mean by that? If I add the 0 matrix by any matrix of the same size, it generates the exact same matrix for you. So the order is not important. Okay, addition between matrices is super easy. Before we jump into subtracting matrices, we're going to talk about the scalar multiplication. So subtraction fraction is stem from scalar multiplication. So let us talk about scalar multiplication a little bit. When you're talking about scalar, you're talking about a number that is multiplied by each entry of our matrix. Definition of scalar multiplication. Definition of scalar multiplication for matrices. So when you're talking about a scalar, we're talking about just a number. It can be zero, it can be fraction, it can be square root, anything. Let A with entries Aij be an n by n matrix. Let K, so I'm going to use a different color, let K basically be a number, a value, be a real number. You can write it this way as well. You can say that, hey, K belongs to R. This bolded letter R, as we mentioned before, represents the real line or negative infinity to positive infinity. We define the scalar multiplication as follows. The scalar multiplication as follow. So take a look. I'm going to multiply K by matrix A. This is the multiplication of K by every entry of the matrix. So your matrix A11, A12, dot, 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 A1n, A21, A22, dot, 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 A2n, and we don't have to list all of these, M1, M2, AM, and so when you're talking about the scalar multiplication, it means that we have to multiply each entry by K. This is what's happening when it comes to scalar multiplication. So basically, you can write the matrix, new matrix, as is exactly M by N matrix. The result is the same. So you have K times A1 and 1, K times A1 and 2, dot, 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 K times A1 and N. You get the same result for every row and column because you're just doing the same thing. You're just multiplying K by each entry. This is A2 and 2, dot, 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 A2 and N. Let me write it a little bit faster. Try to include as many details as I can for you. AM1, AM2, and dot, 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 AMN. And here we are multiplying every single entry by K. So this is called a scalar multiplication. Scalar, as I mentioned, is just a number. So now the question is, if I multiply the entries by -1, what happens? Take a look. Let me write this in shorthand side for you. Ka is equal to K times the entries Aij, M by N, which can be just written as K times Aij each entry. Okay. So now I expect you to ask, so here we have a question. What if we multiply matrix A by k equals to -1 by k equals to -1? And next question is, how do you define subtraction between two matrices? How to use scalar multiplication to define subtraction between matrices. These are all valid questions. When we define some new operation, we have some questions as well. So take a look. If I have a matrix like A and multiply that by -1, it basically just generates the enters of the matrix that are multiplied by negative sign that are opposite in sign. So here you have -1 times Aij, which is basically minus Aij. So we define the opposite entries. Now, if I have two matrices, let A be a matrix Aij of size m by n, and B be another matrix Bij with the same size, then the subtraction or difference between two matrices is defined as follows. Defined as, here you have A minus B, which can be written as A plus -1 times B. This guy is just a scalar multiplication. So basically, what you have the entries of matrix A plus -1 times the entries of matrix B, Bij. So the difference between two matrices or their matrix subtraction can be defined as Aij minus Bij, and this is exactly with the same size. Now the question is, well, if I subtract same matrix from itself, what is the result? So question for you. What is the result of A minus A? If I subtract a matrix from itself, what do we get out of it? Please type in the chat. What is the object that you're going to see? Basically, what is the mathematical object that you're going to have? Very good. The result is not number 0. The result is matrix 0. Take a look at it. So if you write matrix A, and the rest of the terms, AM1, AM2, dot, 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 AMN, minus. So I'm not going to rewrite this. Let me copy and paste. Copy and paste here. So if I subtract these two, you're basically having A11 minus A11, and then A1n minus AN, And then here you have am1 minus am1 dot dot dot. So I'm just writing some of the terms for you, minus amn. All right. The result is zero matrix, everyone. 0, 0, 0, 0. So the result is an m by n zero matrix. Remember that. It's not number zero. Okay, now that we introduced this and talked about this, we can talk about an additive identity and also the additive inverse. Additive identity. There exists a zero matrix. This is what does it tell us? There exists a zero matrix, like matrix 0 of size m by n, such that for any matrix like A of the same size, we have A plus 0, which also can be written as 0 plus A to be equals to A. So this 0 is basically your additive identity. Other than additive identity, we have additive inverse. So additive inverse. Again, there exists a matrix. There exists a matrix like minus 1 times A, such that for any matrix A with the same size, so I'm going to mention the size, matrix A plus negative A can be written as negative A plus A, and the result is zero matrix. So these two are called additive identity and additive inverse. For additive identity, we're basically talking about the zero matrix. For additive inverse, we're basically talking about the scalar multiplication of the same matrix by negative 1 or negative sign. Very good. So I expect you to ask, can I multiply two matrices together? Yes, of course. It's possible. We have matrix addition, difference between two matrices, scalar multiplication. Now let us talk about multiplication between two matrices. Multiplication between two matrices. So when we're talking about matrix multiplication, the order is important in a sense that let A be an m by n matrix. Let B be an n by, for example, you can use any other letter here. It can be P, it can be Q, it can be R, anything that you feel comfortable working with. So if you open different books, you might see different letters used here. P, I'm going to use P. So you have a matrix A with m rows and n columns, m rows and n columns. And then for matrix B, you have n rows and p columns. Okay. We can multiply these two matrices together and find the product between A and B, but be careful, not B and A. Just a quick note here. Why is that? Because the number of columns of the first matrix must be the same as the number of rows of the second matrix. That's how you can define the multiplication between two matrices. So what is the operation, right? I'm going to define the entries of matrix A as A, I, J, and here you have M by N, and matrix B. For example, you can use Bij with N by P size. So if you multiply these two matrices together, you're basically generating a new matrix. You can, for example, denote this by C or M, anything that you like. I'm going to call it matrix M, Mij. Okay, I hope. Okay, let me use a different letter because I have M rows and N column. I don't want to avoid any confusion. So let us use matrix T, for example. Makes it a little bit easier to navigate through. T sub Ij. So now how do we define T sub Ij's? T sub Ij's are defined as follow. This is the summation of A I k's times B K j's when K ranges between 1 to, I'm going to use the same color as what I used here. So my K ranges between 1 and N. If you write this in expanded form, this is what's happening. When K is equal to 1, you get A, I, 1, B, 1, J. Plus, when K is equal to 2, what do we get? We get AI2 times B2J. When K is equal to 3, what do we get? We get AI3, B3J plus, and finally it stops at N. So when K is equal to N, we get AIN times BNJ. Very good. So let us go over a few examples for you. You feel comfortable about matrix multiplication. Let's start with easy examples first. Example. What is the product of these two matrices? Is it possible to multiply the following matrices? If yes, find the result. Take a look. I'm going to multiply 1, 1 by 2, 3. Is it possible to multiply these two matrices? This is my first matrix, and this is my second matrix. Can we do that? Please type in the chat. Here you have 2 by 1 matrix, and you have another column matrix 2 by 1. Is it possible to do that? Remember the requirements. The number of columns of the first matrix must be the same as the number of rows of the second matrix. Okay, the number of column of the first matrix is 1, but the number of rows of the second matrix is 2. 1 is not the same as 2. So it's impossible to multiply these two matrices. We cannot multiply these two. So what if I change this? What if I give you 1, 1, and then I write this as 2, 3? What do you think now? Is it possible to multiply these two matrices? A column matrix and a row matrix. Very good. So here you have a 2 by 1 matrix, and you have 1 row and basically 2 columns. So what do you have? You have 1 column, 1 row. Let's see how we can multiply these two matrices. So this is equal to. The product is possible. Remember that. You end up with a 2 by 2 matrix. Okay, 2 by 2 matrix. That's interesting. So what are you going to do? You're going to find the product of 1 and 2. 1 multiplied by 2 is going to be written here. Let me use a different color. Then you're going to find the product of 1 and 3. 1 times 3. Next, you're going to find the product between 1 and 2. 1 by 2. And then you're going to find the product between, let me use a different color. This one, yes. 1 by 3. Okay, this is new. I multiply these two matrices and I end up with a 2 by 2 matrix. So you have a 2, a 3, 2, and 3. So the product of 1, 1 by 2, 3 is a new matrix, which is a 2 by 2 matrix. That's interesting. So now the question is, what if I switch the order? What if I multiply these two matrices? So I'm giving you a variety of different examples so you feel comfortable about the multiplication. What if I multiply the row matrix by column matrix? 1 and 1. What happens here? I'm multiplying two vectors. This is what you learn in calculus. This is the dot product between them. Is it possible to do that? I have a 1 by 2 matrix and I have a 2 by 1 matrix. Hey, am I allowed to do the multiplication? Yes, because this number of columns of the first matrix is the same as the number of rows of the second matrix. But what is the result? The result is a 1 by 1 matrix. Okay, that got interesting. I have a 1 by 1 matrix. But what is the entry? We are following the definition of multiplication between two matrices. Pay attention to the summation notation. So what are you going to do? You're going to multiply 2 by 1, add it to the multiplication of 3 by 1. It's basically the dot product between two vectors. If it's more easier for you to remember this. If you have two vectors, 2 and 3, dot product with 1 and 1. As you remember, if you have A and B, dot product C and D, you get AC plus BD. This is the same 2 times 1 plus 3 times 1, which is equal to 5. So here you have 2 times 1 plus 3 times 1. So the result is a 1 by 1 matrix with 1 entry. That is interesting. So if I switch the order in matrix multiplication, I get 2 different matrices. One of them is this matrix here, which is a 2 by 2 matrix, which is not the same as the one-by-one matrix that I see just right here. So it's very important for you to recognize that if you switch the order of multiplication, you get different results. So as we mentioned before, zero matrix plays an important role. When it comes to zero matrix, if you add zero matrix to any matrix, you get that matrix back. But if you find the product between any matrix and zero matrix, the result is going to be zero matrix. So in general, let me write this for you here. Just a quick note. Let A be denoted by A sub I and J, and it is an M by N matrix. And B another matrix, B I J, and this is N by P matrix. B, two matrices. So again, if I ask you to find the product between these two matrices, to find the product of these two matrices, we're basically writing it this way. A times B, Ij, which is the summation of A Ik multiplied by B Kj, and K starts from 1, and as you remember, it goes up to N, because the number of columns of the first matrix must be the same as the number of rows of the second matrix. You're basically doing this. If you think about the dot product, you're basically writing the entries this way. This is, for example, taking a representative row and a representative column. AI1, AI2, dot, 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 AIN, and finding the dot product between these two row and column matrices, B1J, B2J, dot, 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 BNJ. This basically gives you the dot product. Dot product between vectors that you learned in calculus. This can be written as, well, the same process as you saw before. The very first entries are multiplied together, AI1 plus the second entries, AI2, B2J plus dot, 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 and finally, the last ones, AIN multiplied by BNJ. So that's how we find each entry in the multiplication of these two matrices. So suppose I ask you to multiply these two matrices. Give me the very first entry of the multiplication. Multiply the following matrices. The very first matrix is -1, 3, we have a 4, we have -2, 5, and 0. The second matrix is -3, 2, -4, and 1. Am I allowed to do the multiplication between these two matrices? I have 3 rows and 2 columns. I have 2 rows and 2 columns. So multiplication-wise, I'm allowed to do the multiplication. But what is the first entry of the product between these two matrices? If I ask you to find A times C, what is the very first entry that you're going to write? Take your time, calculate the first entry for me, type it in the chat, then we go over the solution together. What is the first entry? Very good. Get different answers. So take a look. I am finding the dot product between the first row and the first column. This goes here. So take a look. This is -1 times -3 plus 3 times -4. So this guy goes here. Then we jump into next one. We are taking the same row and multiply that by the second column. We're going to write this down here. So we have -1 times 2 plus 3 times 1. Then let us go to the next row. On the next row, I have 4 and -2, which I need to multiply by the first column. Step by step, one by one, we are calculating each entry. So now I have 4 times -3 plus -2 times -4. So this guy is just written here. Now, let me change this to a different color. Okay, here we go. Now I'm going to take this row again, and now I'm going to find the dot product by the second column. And I'm going to leave it here. So here I have 4 times 2 plus -2 times 1. Let us move on to next row. On the next row, what I have the following. Okay, this one is good. 5 and 0 is now multiplied by the first column. We're finding the dot product between them. So we have 5 times -3 plus 0 times -4. Right? Here we go. And now let us move on to the last entry that we need. Okay, let me use this color. 5 and 0 is multiplied by 2 and 1. We're going to write this guy down here. So I have 5 times 2 plus 0 times 1. Now we can do the computation. And please note that we have 3 rows and 2 columns. So this new matrix AC can be written as I have a 3 minus 12. I have -2 plus 3. I have -12 plus 8. I have 8 minus 2. Then I have -15 plus 0 and 10 plus 0. So this multiplication is -9, 1, -4, 6, -15, and 10. We have a 3 by 2 matrix. Perfect. Let's go over another example for you. Example. Let us matrix M be defined as 1, 2, 3, 1, 2, and 6. matrix N is defined as 2, 3, 1, 7, 6, and 2. Can I find a product between M and N? This is the very first question that you should be asking. Is M by N a possibility here? This is 3 by 2, and this is 2 by 3. Can I calculate N by M as well? Can I switch the order between these two? And the next question, are these two matrices equal to each other? So these are the types of questions that you should be asking. Equality-wise, these two matrices cannot be equal to each other because M by N is a 3 by 3 matrix, but N by M is a 2 by 2 matrix. So since, you're gonna write it this way, since the sizes are different, these two matrices cannot be equal. But let us compute each one of them separately. Why not? We're always interested in computing the multiplication between matrices. Okay, let us copy down M. And let us copy down N. And do a multiplication. Okay. So what is the very first entry of the multiplication of these two matrices? Here I have a 3 by 2 and then 2 by 3 matrix. So I expect to get a 3 by 3 matrix. But what is the very first entry of this matrix? Remember that we are basically doing the dot product between rows and columns one by one. Please type your answers in the chat. Very good. Correct answers. So as we discussed before, we're finding the dot product between these two. Let me use this color. The dot product between the first row and first column. This gives you 1 times 2 plus 2 times 7. This is the process that you're taking. Then the first row multiplied by the second column. So you have 1 times 3 plus 2 times 6. And finally, the first row multiplied by the third column. So 1 by 1, we do the multiplication. 1 times 1. 1 times 1 plus 2 times 2. Very good. Then we move on to the second row. The same process, 3 and 1 is multiplied by 2 and 7. Then 3 and 1 is multiplied by 2 and 6. 3 and 1 is multiplied by 1 and 2. Take a look. 3 times 2 plus 1 times 7. 3 times 3 plus 1 times 6. And then you have 3 times 1 plus 1 times 2. And finally, you move on to the last row, 2 and 6, 2 and 7, 2 and 6, 3 and 6, 2 and 6, 1 and 2. So here you have 2 multiplied by 2 plus 6 times 7. Then you have 2 times 3 plus 6 times 6. And then you have 2 times 1 plus 6 times 2. As easy as that. The rest is pure algebra, everybody. So the multiplication of these two matrices can be written as, so you have 2 plus 14, 16, 3 plus 12, 15, and then you have a 5, and then you have 6 plus 7, which is 13, then you have 9 plus 6, which is 15 again, 3 plus 2, which is 5, and then you have 4 plus 42, which is 46, then you have 6 plus 36, which gives you 42, and finally you have 12 plus 2, which is 14. You might say, hey, okay, we can use the definition up here as well, right? Okay, let me just grab this and copy and paste it here and show you how we can connect this multiplication this way with calculating the entries. For example, let me show you how to find one of these entries. Let us calculate the ij. Let me write it here for now. Aij. For example, a 3 and 2 entry. The entry on the third row and second column. Third row and the second column. Let's follow the formula. Basically, we are calculating the summation of A, 3, and K times B, K, and 2. And my K starts from 1, goes to 2. Remember that this is 3 by 2, and this is 2 by 3. So my K ranges between 1 and 2. Take a look. So if K is equal to 1, I have A 3 and 1, B 1 and 2, plus when K is equal to 2, I have A 3 and 2 times B 2 and 2. So let's take a look at our original matrices. A 3 and 1, where is A 3 and 1? A 3 and 1 is located here. This is my 2. Then I'm going to use a different color for you. I'm looking for B1 and 2. B1 on the first row and second column, which is this guy here, 3. Plus A3 and 2. Okay, let me use a different color for you. A3 on the third row and the second column, 6. Multiplied by B2 and 2. Okay. B2 and 2 on the second row and second column, which is 6. So what do you have? You have 6 plus 36, which is 42. We have the exact same entry here. All right. So this is following the basic definition of the multiplication between two matrices using series or the summation notation. So again, for A3 and 2, this is A3 and 2. To calculate A3 and 2, this is basically the summation of A3 and K, B, K, and 2, right? And K ranges between 1 and 2 because this is the number of columns of the first matrix, which is the same as the number of rows of the second matrix. the properties of matrix operations, then we jump into some important matrices. So far, we talked about addition, scalar multiplication, the difference between two matrices, and their multiplication. So let A, B, and C be M by N matrices. Let K1 and K2 be real numbers. So let me move this a little bit here. And K2 belongs to R. So these two are scalars, some real numbers. Then we have the following properties. First of all, you have addition of two matrices and their order is not important. What do I mean by that? A plus B is the same as B plus A. Or A plus C is the same as C plus A. The order is not important. B plus C is the same as C plus B. These are called commutative property of addition. Commutative property of addition. You have associative property of addition as well. For the associative property of addition, it doesn't matter in which order you group these together. A plus B plus C can be written as A plus B plus C. It means that you can find the summation of B and C first and add that to A. Or you can group these together, A plus B plus C. It means that you can group the very first two matrices together, add them together, and then finally add it to C. So again, this is called associative property of addition. Of matrix addition. So that as a matrix. What else we can do? If you find the scalar multiplication, like if you multiply matrix A by K1, and then find the product, scalar product by K2 is exactly the same as multiplying or finding the scalar product between K2 and A, then the scalar product with K1. This is basically the associative property of multiplication. And finally, you can group these together as well. You can find K1 times K2 and then multiply that by matrix A. So we have associative property of scalar multiplication. Associative property of scalar multiplication. If I multiply any matrix by number 1, the result is going to be number 1. So 1 let me use a different color. 1 times A is the same as A times 1, which is equal to A. And this guy is basically your multiplicative identity. As we had the additive identity, this is multiplicative identity. For additive identity, remember that we use identity matrix. I plus A is A plus I, which is A itself. Additive identity. You also have distributive property. For example, if I add K1 and K2 and find the scalar multiplication by A, this is basically finding K1 by A plus K2 multiplied by matrix A. And again, this is called distributive property. We have many properties for matrices. For example, what are the properties of